Hello everyone, welcome back to this series of videos on Diophantus. If you join me for video 2, you'll remember that Diophantus, unlike in modern algebra, only focuses on one unknown quantity at a time, which we're going to call S, because one Greek sign for it looks a bit like an S with a little line over it. In this video, we're going to look at pretty much the first challenge that faced Diophantus in any problem. What part of the problem should you assign this unknown symbol S to? In this video, we're going to focus on the following 4 problems, and I'd really advise you to pause the video and think about how you would approach them before I talk you through Diophantus' approach, because that'll make the latter stand out a lot more if you've tried them. Okay, so we're going to start with the very first problem in Diophantus' work. It's as simple as these problems get, but even here it makes a difference that we only have one unknown symbol. So this is the problem. I should probably mention that Diophantus normally phrases his problems in general terms and then specifies any constants and any special conditions that they need to fulfill. So for example here he talks first of all about the problem being about splitting a given number in such and such a way, and then he specifies that the given number is actually 100. It's a sort of homage to Euclid's way of doing things. I'm just going to present the problems once those constants have already been filled out. Okay, so I guess the natural thing for us to do with this problem today is to say, well, I've got 2 unknowns, so let me give them each a name, x and y. Now we've got x plus y is 100, and let's order those names so that y is smaller, so we can say x minus y is 40. And from here there are 2 main paths. Either you use one of the equations to make a substitution in the other one, so you might say, well, if x is y plus 40, we substitute that into equation 1 and we get 2y plus 40 is 100, and so on and so forth. Or you can simply average the 2 equations and get x equals 70 directly. Well, either way, Diophantus couldn't do this because he only had this one symbol to use. So what he does is just subtly different. He jumps in at assigning s to the smaller unknown, and he describes the larger number as such rather than giving it a symbol of his own. So he gets straight to this substitution that we talked about just now. So in this problem, having one symbol, obviously it doesn't make a huge difference to the method, but as the problems get a bit more complicated, the choice of what to call s can make more of a difference to how neat the solution is. Consider this next problem. Now we appear to have 4 unknown quantities, and it's hard to proceed in that intuitive way by labelling one of them as s. With 4 symbols that would be just fine, but with only one, things get very wordy. You end up saying things like S is the difference between 20 and the second and third unknowns. So the 4th unknown, which is 22 minus the second and third unknowns, must be the same as S plus 2, and so on and so forth. Well, the neat way that Diophantus found to sidestep this is to focus not on any of the 4 unknowns that we're really aiming for, but on their sum, which is lurking just under the surface of all 4 equations. So if you imagine the unknowns as 4 piles, represented here by 4 squares of different colours, and think of the total of all 4 as s, we can express each unknown in terms of s very simply. So for example, the second equation here tells us that these 3 piles add to 22, so the first unknown must be s minus that. And now we have 2 ways of describing the sum, s itself by definition, but also the sum of these 4 expressions. And this equation shows us that s is 31, from which we can immediately derive the solution. Well, incidentally, another way that you could reach s is 31 very quickly is just to add up these 4 equations. That's not how Diophantus does it, but that would be a neat way to do it. Each of the equations is asymmetrical, but their sum is nice and symmetrical, with all 4 unknowns being represented 3 times over. Well, the idea we saw in that problem of trying to find elements of symmetry also comes up in the 2 remaining problems for this video. So first let's look at this one. Find 2 numbers which add up to 20 and whose cubes add up to 2240. Now, one's first instinct might well be to call one of the unknowns s, so that the other one must be 20 minus s. And if you work through it, you end up with a quadratic equation to solve. Now, Diophantus did know how to solve quadratics by completing the square, but he treats it as quite an advanced method that's only used in the latter stages of his work, and we'll see it later in this video series. To get around it in this problem, he has the following cute and I think quite instructive trick, which is to build in more symmetry right from the start. So he actually calls the unknown quantities 10 minus s and 10 plus s. In other words, he's assigning s to half of the difference between the unknowns. It's not an obvious starting point, but once you do it, you expand, add up, several terms cancel, and you get a very much simpler quadratic equation that you can actually solve by inspection. Now, to end with in this video, I've got another example of that idea. The problem is to find two positive numbers whose difference is 4, such that the sum of the cubes is 28 times their sum. Well, again, let's start with the obvious assignment of s, where we call the two unknowns s and s plus 4. We end up with a reasonably complicated cubic, where it happens to be possible to spot a factor. But that certainly wouldn't have seemed easy in ancient terms. As with the general solution of the quadratic that we considered in problem 3, spotting factors to solve a higher order polynomial would be considered an advanced technique for Diophantus rather than a fundamental one. Instead, Diophantus again works in some symmetry to get terms to cancel and to simplify the working. He assigns s to the average of the two unknowns, which are therefore s plus 2 and s minus 2. Now remember that we're looking for positive solutions, so we do need to keep an eye out for s being greater than 2. But from this starting point, everything comes out quite simply, as you can see. And I think this idea of working with symmetry to simplify problems is still a valuable technique where we can learn something from Diophantus' imagination that he had to apply to his problems. Okay, that's it for this video. I hope it's clarified both how Diophantus proceeds with only one symbol by some examples, but also shown the sorts of lateral thinking he uses when deciding how to use his symbol in order to simplify his problems. I'm going to leave you with a few bonus problems to try and solve using the methods that we've seen. In the next video, we'll still be focusing on Diophantus' efforts to simplify his problems, but we're going to move on to substitutions of a more arbitrary kind than anything we've seen so far.